Lesson 3, Non-Uniform Motion, Acceleration, and Velocity Time Graphs. Any change in an object's speed, direction, or both means a change in velocity. This change in velocity is called accelerated motion. Acceleration is defined as the rate of change of velocity. It's non-uniform motion. It's a vector quantity. The symbol for acceleration is a lowercase a with an arrowhead on top, and the units are meters per second squared, or sometimes we use kilometers per hour per second. The equation for acceleration is given below. Acceleration is equal to delta v over delta t, where delta v is equal to the change in velocity, which can be written as v final minus v initial, or v2 minus v1. So if we look, we can expand this equation a little bit more by saying acceleration is v2 minus v1 over delta t. And then we can rearrange this equation for the final velocity, v2. And if we do, it looks like this. This is another way to express the equation for acceleration, and it's a very helpful one because it allows us to find the final velocity for an object, which is a very common question to be asked in physics. Let's try with an example. A motorbike starting from rest with an initial velocity of 0 and undergoing uniform acceleration reaches a final velocity of 21.0 meters per second. In this question, they tell you that the object starts from rest and that its initial velocity is 0. Some of the questions will tell you that the object's velocity starts from rest, but won't say that v1 is equal to 0. It's your responsibility to assume that if it's starting from rest, the initial velocity is 0. And it's undergoing uniform acceleration, reaching a final velocity of 21 meters per second in 8.4 seconds. So let's write down everything that's given. We have our initial velocity, which is 0, our final velocity, which is 21 meters per second north, and our elapsed time is 8.4 seconds. What they want us to find is the average acceleration. So acceleration is equal to delta v over delta t, which is v final minus v initial divided by elapsed time. And we can sub in our values and determine the acceleration. So we have 21.0 meters per second north minus 0 divided by an elapsed time of 8.4 seconds. Let's punch this into our calculators. If you do, you should get an acceleration of 2.5 meters per second squared north. Therefore, the acceleration is 2.5 meters per second squared north. Whenever you have accelerated or non-uniform motion, on a position time graph, instead of it looking like a straight line, we get an upward curving line. This upward curving line tells us that the motion is non-uniform, that the object is speeding up, that the object is accelerating. Similarly, we can get this downward curving line in which it's steep at the beginning and not steep at the end, which means its velocity is decreasing over time. This is what accelerated motion looks like on a position time graph. Speeding up and slowing down. For speeding up on a position time graph, an upward curving line, and for slowing down, a downward curving line. We are going to introduce a second type of graph, an important one when studying motion, and it's called a velocity time graph. So a velocity time graph is one in which there is velocity on the y-axis and time on the x-axis. So let's take a look at a couple examples of velocity time graphs. So take a look, velocity on the y-axis, time. And here we have an object that is speeding up, and this is what a velocity time graph for an object speeding up looks like. It's a straight line with slope. So we can actually find the slope of this object speeding up. And we know that the slope of a velocity time graph is equal to the acceleration of an object. So we can find the slope of this graph, delta y over delta x. Since the y-axis is velocity, then we have delta v, and the x-axis is time, we have delta t. So we pick any 2 points and we do v final minus v initial divided by delta t. So let's look at a couple points. I'm going to pick t equals 1 second, this point, and t equals 3 seconds, this point. And from the table, we can see t equals 1 second and t equals 3 seconds, and we can use these values to find the acceleration. So the final velocity is 18.0 meters per second, which we can either read off the graph or more precisely take from our table of values. Please include the direction. In this case, it's west. We're going to subtract from it the initial velocity, which if we read off the graph or look on our table of values, we see is 6.0 meters per second west. And our elapsed time, we're going from 1 second to 3 seconds, so 3.0 seconds minus 1.0 seconds. And we can proceed to answer this algebraically because both the directions are the same. They're both west. If they weren't the same, then what we would need to do first is to change them so that they are both the same. Okay, let's punch these into our calculator. 18.0 meters per second west minus 6.0 meters per second west divided by 3 minus 2. We end up with 6.0 meters per second squared west. So we found the acceleration of this object by finding the slope of a velocity time graph. In fact, that's a very important thing to remember, that the slope of a velocity time graph gives you the acceleration. So write this statement here and highlight it so that you can remember it when you're looking over your notes. Let's take a look at a velocity time graph for an object that is slowing down. If you take a look at the characteristics of this graph, it's a linear relationship, there's a straight line, but it's downward sloping. This downward sloping tells us that the object is decelerating. Let's find the slope we know it's slowing down. We call it deceleration. I'm also going to give it a different name, but I'll tell you what that different name is after we've done calculating the acceleration. So we'll pick any 2 points on the graph. We are going to find 1 second, which is here. If we read it off the graph, we'll see that the velocity is 18.0 meters per second east. And then we'll take another one at 3 seconds. If we read it off the graph, we can see that the velocity has reduced to 6 meters per second. So slope delta y over delta x is change in velocity over change in time, which is final velocity minus initial velocity over t2 minus t1. Let's sub it in. Remember not to mix these up. This is our v final, this is our v initial. So we have 6 meters per second east minus 18 meters per second east divided by 3 seconds minus 1 second. Punch it into our calculator, 6 minus 18. We end up with negative 6.0 meters per second squared east. This negative sign, when dealing with an acceleration, tells us that the object is slowing down. So the acceleration is negative 6 meters per second squared east. Deceleration is also called negative acceleration. Okay, so we've seen what speeding up and slowing down looks like on velocity time graphs. We've also looked at the equation for acceleration in general, and we've done some sample problems. What I would like you to do now is to work on the homework practice questions given below, and then complete the LMS quiz on your course homepage. Good luck.